Welcome to a lesson with Dr. Pal. Let's investigate the convergence or divergence of this particular series by using a limit comparison. Let's get rid of that part right here so we can think of leading terms just for a rule of thumb. It looks like square root of n over, in fact, let's just compare it to, let's just think of what this is, n. So this kind of looks like 1 over root n, because this is n to the 1/2, n to the 1, and it simplifies to this 1 over square root of n, or n to the negative 1/2. So this value right here, p, is less than 1. So so it has this kind of schematic when it's less than 1, diverges over here, the integration converges over here. So since series always go this way, it diverges. So let's see if it diverges, but let's do it with a limit. So the way we do that is we just take a ratio of this to this. And it doesn't matter what goes on the top and bottom, we just have to interpret our result differently. A limit as n approaches infinity. So we can rearrange this, maybe multiply top and bottom by 2n. So if we multiply top and bottom by 2n, then we end up getting 2 root n on the bottom, and that, which we can interpret as 1/2 square root of n plus 2 over n. Now the limit, square root is continuous operation, so limit can bounce on the inside. Take a limit of this. Now this limits to 1, which means that the whole limit right here limits to 1/2. A half is a constant, and so that means that eventually this is like 1/2 of that, which means eventually this is like less than that, or even, but if you multiply this by 4, then eventually 4 times this would be bigger than that. So really the inequality could go both ways asymptotically, because we're getting a constant and we didn't get 0 or infinity, we just got a non-zero constant, which means that the divergence convergence of this is the exact same as if we were looking at this, which we already know will diverge. Hence, this series will diverge by a limit comparison test. Thanks for watching.